associated professor, and her research activities focus on pathogen ecology, interlinking functional genomics, and prediction of microbial behavior. She is active as editorial board member of Food Research International, International Journal of Food Microbiology, and Journal of Food Protection. She is also a member of the program committee of the International Association of Food Protection, and she teaches within MESc and BSc food courses in Wageningen University. So Heidi, thank you so much for accepting to join us in this webinar. So it's with you. Thank you so much.
Many thanks, Anderson. Do you see my shared screen?
Yes, yes.
Yes, great. So many thanks for the introduction, and it's my pleasure to introduce you to the education we do in Wageningen in the field of quantitative microbiology. And actually we are active in this field not only on our campus education, but also online education. And I want to give examples on these both pillars actually of our education today in the webinar. So when students finish their secondary school, they can come to Wageningen and starting their bachelor in food technology, which runs 3 years. And when they start in this course, they also already get introduced to predictive modeling and also quantitative microbiology. So after completing the bachelor, they can also continue. Most of the students, they do continue with a master, and they can choose either food technology or food safety. And in both master programs, also elements of quantitative microbiology are integrated. And our philosophy in Wageningen is to integrate this area of quantitative microbiology in the whole curriculum, and not just in one course, but we make stepping stones through the whole curriculum. And I will give examples of that today. So as I said, when students started in their bachelor, the first course they do here in Wageningen in the field of food microbiology is called food microbiology. And also there already, they are introduced to aspects of quantitative microbiology. They're going to learn what is a primary model, secondary model, texture model, and how to model also growth. They're going to learn what is the specific growth rate and how to calculate it, parameters of the growth model. Also, they're introduced to the gamma concept, how to predict growth rate based on the environment or based on food characteristics. But next to aspects on growth, they are also introduced to aspects on inactivation. So what is a D value? What is a Z value? What is an F value? How to calculate these phenomena and how to apply it. So after their bachelor, the second course they are introduced or they build on in this area is advanced food microbiology. And there they are really using the gamma concept. They're going to use it to predict what types of organisms are the main associated spoilage organisms in food. They are really going to use the different gamma models. But also they're going to extend in the area of inactivation. So how to deal with inactivation curvatures which are nonlinear, how should you treat them, and how can you use, what kinds of models are available to fit nonlinear inactivation data. Also, they are introduced to what is a quantitative microbiological risk assessment. So what are the 4 steps in this risk assessments, and what elements are also in a risk assessment which needs this predictive microbiology approach. So after this advanced food microbiology course, they can continue also with the course food safety risk assessment. And this again, in this course, the topic is broadened. They learn more, but also on some aspects, they go deeper. So it's really as a stepping stone, as what I told in the start, how we build the education. And in this food safety risk assessment course, they are really going to do a quantitative microbial risk assessment, not only for microbiology, but actually also for chemical risk, for toxicological risk. And they're going to use available quantitative microbiology programs. For example, PMP, they're going to use in their exercises, and also they're going to use the gamma model. And there they also see that when you use other models, you have to assume things. You have to, we are training them to dare to assume, because, for example, if you use the PMP model, maybe the product type you want to use to predict microbial kinetics is not available in a specific program. So you have to assume what is the best second product which you can use for your predictions. And then the final big course we have, concluding our master program, is food safety management. And in this food safety management course, not only students with a background in food microbiology are joining, but also students with a background in law and students with a background in logistics. So the groups are really diverse. And in this course, they have different groups where they also have different roles. So students take the role of an industrial, from the industrial perspective, or from the governmental perspective, or from the consumer perspective, and they are going to use QMRAs to make advices on how to deal with emerging risks. So what kind of intervention strategies you can take. And then in the middle of the course, there's also a crisis. A crisis happen, an outbreak, a chemical risk outbreak, or a microbiological associated risk outbreak, and they have to deal with this crisis, which runs for one day, and then they have to apply to this crisis in their role as an industry member, or in their role as governmental representative, or in their role as consumer representative. So they learn really how to, on management level, how to deal with these situations. This is a really play situation where they train different roles in food safety management. So this is just a short overview of our online education, so on bachelor level and more advanced on master level. But last years, we also made a lot of progress on online education. I just forgot to mention that, especially also in the master courses, there is also room to introduce students to upcoming research fields. For example, in advanced food microbiology, we also give lectures on biomarkers. So how we can use biomarkers and what are the challenges actually to find biomarkers for robustness, and how to quantify stress response, and how to what is the route to integrate this like phenotypes also in exposure assessments. So next to the regular courses and the regular lectures we have also room for some extra lectures which can make a clear link to upcoming and new fields of research. I already shortly mentioned it, that we, next to the campus education, we also have built online education. Actually, we have full programs online, which are a MOOC and SPOC, and also an online master in food technology. And I will shortly introduce the terms to you, because what is a MOOC? It's a massive open online course, so for a big group of people online. And what is a SPOC? It's a small private online course. So what are the main differences between a MOOC and a SPOC? Now, a MOOC is massive, so it's designed to support an unlimited number of students and, of course, open access. But a SPOC is really limited with respect to the number of participants you can have. But it also allows to combine it with live campus activities. So it can be used as really blended learning. So next to campus activities, also online activities. So we have built 3 complete programs online, and SPOC on food technology, a MOOC on food safety, and an online master in food technology with a specialization in food safety. So first, the SPOC on food technology. And this actually we designed together with the 4 other chairs in our food science cluster: food chemistry, food physics, food engineering, and quality and design, in collaboration with the Nanyang Technical University in Singapore. So we are teaching this course for students in Singapore. And each of these 5 courses, they run for 13 weeks, study weeks, and the students are introduced online to knowledge clips, short clips 5 to 10 minutes with covering a complete topic, and then also exercises so students can practice this the knowledge they learn in the knowledge clips. We also have designed digital assignments, which are really dry lab practicals. So we simulated practicals digitally, so they also have the experience of like the lab environment, but they do it on their own in their own office. And we also meet students on a weekly basis during live question hour. And as I said, we still have this physical interaction because we have online practical courses. So we really go to Singapore for teaching the practical course. And here you see a screenshot of how the course material looks like. So every week we have materials also on quantitative topics, because this course we give in Singapore is basically the online copy of the best bachelor course we are teaching here in Wageningen on food microbiology. So it's the learning outcomes are exactly the same, just the way of teaching is different because it's fully online. So this is a picture of my colleague Marcel Swietering, who is teaching here on the microbial growth curves. So students are watching to these clips, short clips, and then they are exercising, like the theory they have learned. They finishing or they're working on exercises. They get feedback, so they learn on their own pace. They can do it as many times as they want to really practice to get into the theory. So this is just a short like overview of the SPOC, so the small private online course. But next to the SPOC, we also have the MOOC, so the massive online online course in food safety. And this has been designed online, but actually we also use it in Wageningen on our campus in a course. So it's also enriching now our on-campus education, while on the first instance, it's what's designed really online. So this MOOC is available on the platform edX. You see below the link. Everyone who wants to join, can subscribe. It runs more than once every year, and students from all over the world can just join this MOOC. And it contains of 8 different weeks. The last week is the exam week, but in the 7 other weeks, they're dealing with all kinds of topics, also in the field of predictive modeling and quantitative microbiology. As you can see, what is the difference between hazards and risk? What are the stepping stones of risk assessments with respect to toxicological risk, but also microbiological risk? And also here they're learning through watching knowledge clips, which are all subtitled. And they also looking to animation, so it's really blended different types of education forms. And also here they learn the theory by making all kinds of exercises. And the most favorite element of the MOOC is always the myth of the week, which is a very short movie about a myth. And for example, here you see a screenshot of our French chef, who is saying that when you look to the Listeria monocytosis cases in America with respect to raw milk and pasteurized milk, you see lower number of cases for raw milk. So he said, is it then true that raw milk is safer than pasteurized milk? So this is the myth of the week. And then this is like also the discussion point of the week. Students can discuss amongst them to discuss this myth of the week. So last but not least, we also have developed an online master in food technology with a specialization in food safety, which is dealing with microbiology, but also with toxicology. And again, it's comparable to the learning outcomes of the master we have here in Wageningen. And it has a clear, as I said, a specialization focused really on food safety. And it also includes the course Advanced Food Microbiology, which we also have on campus. But then we don't have the practicals on the campus, but we have for this online master, we have designed a digital lab practical. And for example, in this digital lab practical, they're going to predict the shelf life of different foods using the gamma concept. So they have been introduced to the gamma concept, and they're really going to use it to predict how long the shelf life of different foods is. So they're really going to also to apply this knowledge in the field. So as a short summary, we started like 30 years ago, basically in Wageningen, to integrate computer work in our education. In the last 5 to 10 years, we really make complete programs, and we try to make also the link to integrate elements of these online programs also in our online campus activity, and which makes it a really blended learning activity, because the knowledge clips, for example, we have designed for our students in Singapore, we also use for our campus students, because they can rewatch these clips how many times they want, which is for them a very good learning experience. And also in Wageningen, you can see a picture at the bottom of one of our big lecture halls. Also, all our campus lectures are recorded, so students, if they want, they can also view the lectures at home. And it's live broadcasted and also stored. And especially this last item, that storage of the lectures is done here in Wageningen, was really nice in the COVID times we had, because we could rely back on the storage we had of the lectures. So when the students are finishing their bachelor program and their master program, the finishing masterpiece of bachelor piece is their research project, their master research project, or their bachelor research project, and which takes 4 for a bachelor and 6 months for a master. And here we really try to make the link to research, to PhD work. So PhD students, they host master students and bachelor students in their project. They learn to supervise students, and the students, they learn from like cutting edge research topics. And we also use theses to explore new topics. So topics we might want to write a project proposal later on. We also try to set first stepping stones together with thesis students on these explorative topics. So to conclude, the field of quantitative microbiology is really integrated in our whole curriculum. It starts in the bachelor, and we build on in our master program. We broaden it in the courses in our master program, but we also deepen several topics to a great extent. And we have these 2 pillars, the online and campus education, and we really learned that the activities we do for online also enrich our campus education. And as I said, we were really happy in these COVID times that we have made a good big steps last year's online, because we could use it in a very quick change from campus education to online when COVID came in. So having said that, I think I give the floor back to the moderator, Anderson. I'm not sure if it's good to take questions now, or you want to save them for after the last final presentation.
Thanks, Heidi, for your very nice presentation. We are going to take questions at the end, when all the speakers are done with their presentations, okay?
Yes, thanks. Yes. Good.
Thank you so much. So we are now moving to our next speaker, which is Huta Hanta. Dr. Hunter is a senior expert on Bayesian modeling and biostatistics at the Risk Assessment Unit of the Finnish Food Authority. His PhD thesis in biostatistics was on Bayesian modeling of human disease epidemiology. He has then worked on quantitative food safety risk assessments at the Finnish Food Authority and continued part-time teaching at Helsinki University. So Huka, thanks for joining us. So it's with you now. Thank you so much for being here.
Okay, thank you. So I'll just quickly try to share the slides and move on. Okay, so do you see it?
I cannot see it yet. Ah, now it's there. It's there.
Ah, okay, it's good now. Okay, so let's see. So my presentation is about some aspects about using predictive microbiology models in a food safety agency, and maybe some examples of our work, and then, well, some ideas about possible future. So if I remind about some usual tasks of a food safety agency, then they're usually about setting or adopting guidelines and requirements for food safety nationally, or interpreting general international requirements in a specific national context. And sometimes it could be about contributing to a proposed legislation updates or current laws. And then there are sometimes international cooperations with other agencies and EFSA in Europe, and also some research organizations, both domestic and international. So, and as it also mentioned about the connections that there could be to the international organizations, both within regional context in Europe and in the world. And not to forget the animals and plants, because our agency is not only concerned about food, but also animal and plant safety and plant health and animal health. So maybe I could say that many of the tasks are finally leading to microbiological criteria, because if the authorities set the microbiological criteria and then they secondly enforce the agreed criteria. And in contrast to that, then food business operators may develop new products, and then they find out how they can meet those criteria that are required. And in doing so, they may utilize predictive microbiological models that could be available for specific hazard food combinations. But from the point of view of an agency or national agency, I guess the common approach is straightforward adoption of the Commission regulation, which already lays down the criteria. So many times it's just citing these regulations and just adopting them in the national context and giving guidance on those regulations, which can be found from this link, for example. And sometimes these are, of course, updated, and then national agencies could be required to give comments or suggestions to the updates when those updates are done. But then about those criteria, it could also be said that one size does not fit all situations, even with those general recommendations, so that there could be exceptions to the general rules, which may require further assessment. And so even though predictive microbiological modeling may not be used on a daily basis, but it could be used on demand in such occasions where some further assessment is needed. For example, when there are some exceptions to those general rules. And those exceptions could be, for example, there are exceptions for small businesses, for small operators, and one exception is also that if there is national or regional salmonella control program in place, and if that is accepted as a replacement of those microbiological testing sampling rules, then this could actually be used instead, and then depends on what's there in the control program. Then a national agency could be required to assess how that actually complies and how is it equivalent to the general requirements. So sometimes the government may ask us to make such evaluations to compare and to somehow see how these things are compatible. But also the requirements might sometimes come from the food business operators because they might provide some new evidence for particular products or processes based on some alternative sampling schemes, or and those might be based on predictive models also. And so sometimes the agency might be asked to comment or to evaluate such alternatives. So in that kind of situations, the probabilistic models could be used, for example, to model the concentration distributions and to model the control sampling as a statistical model. And they're also possibly using predictive models that could start from the last control point of the criteria to predict the actual consumer risks. So these are some occasions where this actually could come in use. And then there's the question about the uncertainty of those criteria. And because the probabilities for the acceptance or rejection according to a criteria, often these calculations can be started by assuming the parameters for the pathogen concentration distribution. And of course, in reality, we cannot know exactly what those parameters are. These can be different for each country and each production system. And so we can only basically have some baseline data from control programs or surveillance data that we can use to evaluate the uncertainty of these parameters, and then try to assess that what's the consequence for the criteria and the performance of those criteria based on the most likely parameter values. So we can try to evaluate the uncertainty distribution for those acceptance percentages in this situation that we have based on the baseline data there, and then try to estimate what is the relative risk reduction in that case, which can then lead to assessing what are the probable costs and probable benefits of such a system in place. And this is one picture of one of those studies that we did, where you have the probability of rejection in the x-axis and then the relative risk reduction in the y-axis. So using the baseline data and then knowledge of the outcomes of those samplings according to the criteria in place, using both of those data, one could probabilistically update the risk estimate that concerns the accepted batches to examine the probable risk reduction and the residual risk that still would remain. So taking into account the uncertainties in the data. And there's one paper about Bayesian application of such uncertainty computation. And then the other situation of using predictive microbiological modeling is probably that would be in the case of QMRI assessments that sometimes are done in the national agencies. So if there is a national risk assessment of a particular production chain or part of it. And so those could deal with the whole farm to fork chains or part of it. And it's usually a question of one specific pathogen like Salmonella or Campylobacter, and then some specific meat production chain or even several different production chains if the same pathogen is somehow prevalent in all of them. And so this can be quite large and intensive projects to build the farm to fork chains and assessments. And then, of course, predictive microbiology model could then be a part of the whole assessment, but not the complete assessment as such, because there are these other elements like primary production, where you could have animal infection models and so on. And then, of course, you can imagine that there are practical constraints, the time pressure and the resources available and data and the complexity of the problem. And all of those will influence on what actually should be done. And so the drivers for modeling choices maybe could be about identifying which are the biggest uncertainties, and to identify which are the most important variabilities to concern. And then, of course, the question that is there a possibility for microbiological growth in a specific process step or product at all, and what is the most relevant aspect for the risk, and what actually needs modeling, and so there are many different variabilities and uncertainties at several levels in the farm to fork chain. And if all of those have to be somehow assessed and even quantitatively, then we can ask that can we even model all of them, and should we, and what things we actually should model, and where the modeling could be most useful. And in doing the models, then of course we try to take into account to model both the variabilities and uncertainties with a probabilistic approach. So basically, these QR models almost every time they require some kind of quantitative evidence synthesis, because there are different data sources that have to be combined. And so there are practical limitations from the data that, for example, if you have only constant values in a data in your measurements, then you cannot estimate variance parameter from such data. And then what can you do then for the assessment? Use some other data or assumptions. And it's also the case that all the data that would be somehow necessary or important will never be in practice obtained. And then what can we do? One option is to simplified models, or maybe perhaps to try to use models for missing data. So that contains all kind of imputation models and Bayesian inference model for trying to model the kind of the missing variables in between. And this could be useful, for example, in hierarchical models to study between study and within study variations, like in meta-analysis, and use the whole ensemble of data to estimate all the parameters. And so you could use that to maybe get some reasonable estimates for data per units, and also to use indirect probabilistic evidence to estimate uncertain parameters in connection with each other. So this picture describes that if you have three parameters, then there are not three independent uncertainty distributions, but one uncertainty distribution that is three-dimensional. And so there is actually information in the combination that there are some combinations of parameter values that are more probable than others. And these kind of things can be evaluated with these models. So in short, dealing with both variability and uncertainty in a more holistic way. So simulations of exposure and disease burden is sometimes asked, and the difficulty with bottom-up models is that when you try to predict population risk, then you have a lot of uncertainties on the way in the whole production chain, and this may result to very unrealistic predicted disease counts. When you compare that with the reported cases, and then the question is that how can you then adjust your model that it somehow matches the reported epidemiological data, and how do you do this kind of adjustment to adjust which parameters? This is not an easy question, and or you could try using only relative estimates instead of absolute risk estimates. But one possibility there again is to use the kind of holistic network model approach, that you could try to combine both bottom-up modeling with top-down modeling as a probabilistic network to somehow draw evidence from all the sides. And as one example, there is what we did with Listeria, and this couple of other references have done similar things already before. And so just a very simplified picture of the network that combines the occurrence data about the pathogen in those food products, and also the consumption data, and then the predictive microbiological model for the growth, and then the dose response model with an parameter in that model itself, and then finally the reported case data about the disease cases. And this is one image from this assessment that it's not only about trying to estimate the probability of infection on day 5, assuming that somebody will consume a product after 5 days growth, and so there would be some risk after such long time. But when you also take into account the probability of actually consuming it on day 5, then you have consumption data which tells you that it's very unlikely that somebody would consume it after 5 days. And when you combine this in the probabilistic model, then you get the combined probability of the actual probability of illness, which then becomes low, because it's even though the growth will increase the risks, but then on the other hand, the dynamics of the consumption habits will actually press the actual probabilities down, because it's unlikely that nobody would consume it so long. So okay, so the last point is to maybe sketch some things about the future. That one aspect would be to make better interfaces for this model, to have them better interoperable and shareable, and maybe also more intelligent tertiary models that would somehow automatically choose model structures based on the input data. And then the question of sharing the models, for example, in the RAGIP system, that could be used as a model repository for documentation of the models and execution of the models and sharing the models. And not only RAGIP, but there are other possibilities, of course, like R packages and Shiny apps and so on. Okay, so that's my final slide. Thank you. And I maybe also say that there may be questions after the session is over. And I give back to the chair.
Thank you, Huka. We are going to have questions at the end. So now we are going to move to the next speaker, which is Dr. Marianne Eloise. Dr. Marianne is a senior microbial risk assessment specialist at the Institute of Food Safety and Analytical Science at Nestlé Research in Lausanne, Switzerland. In her current role, she evaluates existing and new products, processes, and concepts, provides technical assistance and scientific advice, and develops tools and guidelines to help Nestlé research and development centers and operations to conduct microbial risk or exposure assessments. She is the project leader of the ISO working group on cardinal values. She has animated different workshops and webinars, participated to different conferences, and wrote several scientific publications on the topic. Dr. Elows has contributed to ICPMF achievements by different activities during her service of 2 years as ICPMF secretary from 2015 to 2017, and as ICPMF chairwoman from 2017 to 2019, co-organizing the ICPMF conference in 2013 in Paris, setting different workshops to export the software fair concept to other conferences like IAFP, United States, Food Micro, Berlin, Germany, and Dubai Food Safety, DIFC in Dubai, giving trainings to different groups and authorities, such as the Danish authorities on the acceptance of predictive microbiology tools. So, Marianne, it's with you. Thank you so much for being here with us today.
Good morning or good afternoon, everyone. Can you all see me and see the shared screen?
Yeah, I can see your screen.
Excellent. So thank you, Anderson, for the introduction. I'm really pleased to be here with you today and to see this initiative of the Young ICPMF taking shape. So today I was asked to talk about present and future of predictive microbiology in the food industry, to give some examples and share with you some challenges. So this is the brief outline of my presentation. I'll be talking about the present, the future, and coming with some challenges and maybe raising some questions. So what is the present situation? Well, you all know there are many possible applications of predictive microbiology within the food industry. I'm not going to detail them all today, but I will pick some case studies. Starting with the first one, I would like to show you how it can be used and is used to support in formulation and shelf life setting. So let's imagine that we have a chilled product with these characteristics. Of course, pH is important, but other aspects are also important, like the concentration of preservatives, what is the expected shelf life, what is the targeted market for this product, and if we have a specific packaging. So here the question was that we had a request from the sensory team that proposed to increase the pH of this product from 5.7 to 6.2. And of course, we anticipated that it would have an impact, but is this impact acceptable? That was the question we had. So here, as it's a chilled product, our main concern was Listeria monocytogenes, and we wanted to use FSSP, which is a software that you might know. And we had to make some hypotheses to echo a little bit what Heidi said in her first presentation. We always need to make some choices and to dare to make those. So here the initial contamination was set to 1 CFU per gram, equaling to 0 log CFU per gram, which is from our data a reasonable approach. So if you're not familiar with the FSSP software, this is how the interface would look like. So you could introduce here in the first product the characteristics of what you would like to have for your historical simulation or simulating the historical product. And here is the change with this shift in pH to 6.2. So this is the outcome that is proposed by the FSSP software, and here we can see in red the expected growth or non-growth here of Listeria monocytogenes over the 40 days of shelf life, so in red, and the product number 2 is represented in blue, and here we can see massive growth, so exceeding 5 logs for this same product if we increase the pH to 6.2. There are other aspects that we can focus on from FSSP, which are the psi value that you can see here, which represents, if you wish, a summary of the hurdles that you are putting in place to prevent growth of Listeria monocytogenes, and the highest, the psi value, the best is your combination of hurdles to avoid Listeria growth. So we can see that with product number 2, we have decreased dramatically the psi value. You can also see in the FSSP the time for the 100-fold increase in Listeria monocytogenes population. In the first case, it was not reached because we had a flat curve. However, in the second case, after about 15 days, we would reach this level. So this is linked also to the microbiological criteria, at least in Europe, linked to this pathogen. So we could play around a little bit with the software and see different options. And here, what we can see from the table is that, so the first two cases are product as it is now and the product with an increased pH. And then we wanted to see the impact of adding some amounts of acetic acid. So it was not possible to have this amount of acetic acid and to keep the pH at 6.2. So we had to trade off at 6.0. And with this, we could control Listeria monocytogenes with no growth, but as you could see, the psi value is a little bit lower, or really lower than the initial one. So we wanted to improve this a little bit, and this would take us to have the same psi value as the initial case. We would need to increase dramatically the acetic acid concentration, which may not be compatible with the sensory objective. So this is just to show you how you could play around a little bit with the software and how you can, in fact, interact with these types of requests. We had also other types of requests like go and clean label, and in this case, if we want to get rid of the preservation systems, or at least the chemical preservatives, we could do the same, and you could have additional simulations done where we can prove, for example, that if we take out the sorbic acid, the benzoic acid, and the citric acid, and just remain with the acetic acid, we could have an acceptable situation. But of course, the sensory needs to be considered. And something important here is that we remember I said this was for a specific market, and this was kept at 5 degrees. So let's see now the impact if we want to produce this product for other types of markets. So as you may know, different markets or different countries have different chill chain, and you need to take this into account. So for example, here I took the example of France and the Netherlands. They have two different scenarios. For France, it's 1/3 at 4 and 2/3 at 8. For the Netherlands, it's 2/3 at 7 and 1/3 at 9. And the good news is that with our reformulated product, we could ensure not to have growth in Listeria monocytogenes. So this is ending the first case study that I wanted to share with you. Going quickly through the other ones. So for the second case is often something we receive. So request for technical assistance in the case of process deviations. So factories operate according to very strict rules, and usually when we have storages before sterilization or heat treatment operations, the temperature and time of those storages are really well defined and controlled. In this case, we are seeing a deviation that was noticed by the quality team, but that was noticed only after the sterilization happened. And we can see here the profile of this deviation. So the question is, of course, is there a food safety concern linked to the batch that encountered this deviation? So in that case, we would not be able to conduct microbiological enumerations, of course, because we only realized that there was a deviation after the heat treatment was performed. So we would not be able to find any organism. You would say, okay, but then there is no concern. I would say no, because maybe there was some toxin producers in this batch, and they could have grown to level to produce toxins before they are inactivated. So here I'm showing you an example with Combase. So we have two situations because the pH of those products go from 6.9 to 7.3. That's why you have two simulations here. You have the time temperature profile, which is put into the software and represented here in the graph with this red curve. And then you have, of course, the simulation of microbial behavior in orange for the 7.3 pH and in purple for the other pH. So what this graph is telling us is that if we start from an initial concentration of 2 logs, and in that case, I forgot to mention, but I took Bacillus cereus as a representative of toxin producers. If we take this 2 log as an initial contamination level, then we are going to reach levels of concern, which are here put by this bar, and we are going to exceed this at the end of the storage that we had. However, keep in mind that this simulation was done in broth. And so in culture medium, we don't have a very true picture of what happened in the real matrix. And keep in mind also that our concern was the toxin. So the simulation of the growth is only an indirect assessment of what could have happened. And we know from our research that toxin production, for example, does not happen at temperatures below 12 degrees. So this is a kind of fail-safe evaluation, but when you need to take a decision, you need to be really informed about the limitations of the tools that you are using and all possible information that you can have at hand. So this example and others sometimes triggered the food industry to go and investigate a little bit more and invest in research projects where their objective would be to, of course, build knowledge and address immediate questions and needs, but also to anticipate future requests. So I'm sharing here just quickly outputs from a stream that we had in a project that recently closed. So we were able to characterize different strains of Bacillus cereus for their emetic potential, but also for their cardinal values for different factors. We were able also to act on the analytical side to improve our knowledge on the quantification of those toxins, and based on that we built a model that was published recently, and we also built operational documents that we called heat maps that we can give to our operations so that they can identify safe areas of formulations in their normal operations or also in cases of deviation. We also produce simplified worksheets of those knowledge building that we are doing so that our colleagues can have the information immediately. This work was also used after the project closed and used in predictive microbiology models, again, in order to estimate if it's possible to increase cleaning times between two shifts in a production facility. So this is a very important point in the industry because cleaning is very important, it's crucial, but it's also taken time. So when we can prove with a scientific approach that this cleaning time can be safely increased, it's a lot of interest for the industry. In that case, for example, we could increase the line productivity by 30% without engaging in new experiments. Now, let me talk about the future. And from what maybe we have already seen in the previous presentations, or from what you have already seen in your readings, the future is already here. It's just evenly distributed. So I'm going to talk about the next generation of microbial risk assessments or exposure assessments, and the previous speakers touched a little bit on this, so I'll be quick. And I'm going to talk about the concepts of variability and possibly uncertainty, and give you some insights on what, or elaborate a little bit more on what was previously said. So the next generation of microbial risk assessment or exposure assessment is basically about connecting the genotypic characterization to what we have now in the ways of working regarding risk assessment or exposure assessment. So I will be quick on that one. I would classify those in three main groups according to their readiness. And this is my own opinion. Maybe you have another one, and I would love to debate with you on this after that. But there is a group which has, for me, immediate readiness, and those are the studies where we have genotypic characterization that is directly linked to growth or inactivation, because we know how to wire those into the actual systems that we have for risk or exposure assessment. An intermediate readiness level would be for those studies that are bringing genotypic characterization to investigate the virulence, the subtyping, or the antimicrobial resistance. And then one that is maybe less ready to be wired to our existing systems on risk and exposure assessment would be the studies that would look at complex microbial interactions from a genomic perspective, the metabolic functions, the protein expressions, and so on. So there are attempts that have been made, and I've seen that in the literature. However, coming from an operational side and how to put that in practice in the industry seems to be, for me today, not immediate. I'm going to leave you for this part with a quote from this paper from France. It's a bit old now, but I like it very much, which says the integration. He was talking about whole genome sequencing, but maybe we can also talk about all the next generation approaches. So this requires a paradigm shift and involves to generate a measure of risk that matches the requirements of food safety authorities and policymakers. And this makes the link with the second point I wanted to discuss with you today, which is to consider the variability and possibly, and if possible, the uncertainty. So this has been done for many, many years now, more than 2 decades, but it's still not a trivial exercise, at least on the industry level. And I'm going to illustrate this with the last example. So let's say that we are producing for the European market this product with a shelf life of 10 days, and we know that this product supports the growth of Listeria monocytogenes. So based on the EU regulation, and we've had a discussion or presentation on the microbiological criteria before, we have two options here. Either we can demonstrate that we cannot reach 100 CFU per gram at the end of the shelf life, but of course I cannot be it cannot be free. It needs to be coupled with a sampling plan, and this is given. So we need to ensure we have 0 samples that are that are exceeding this level with a sampling plan with n equal to 5. Or we need to ensure non-detection in 25 grams. I did not say absence. I really say non-detection because I think it's more appropriate with the same sampling plan. So we have two options to answer or to make the assessment. We could run microbiological tests, which would be the preferred option. And predictive microbiology and simulations are listed as an optional tool that we could use to ensure or to answer to this question. So if we are running microbiological tests and we are obtaining this C equal to 0 for 5 samples, then we can say that this is 0%. So the decision is simple. We can accept the batch. However, which is not said, but what we do know is this 0% is in fact associated with the confidence interval from 0 to 46%. And if we assume that there is a prevalence of 5% in our products, then this would mean that we could accept non-compliance and we could accept this batch that is non-compliant with a probability of 80%. If we run the simulations, we can have this type of outputs. This is a completely different output, and this was obtained with SimPrevious. And if you are not familiar with this, I'm going to take you through this graph. So we have the growth of Listeria monocytogenes over time. You have the red curve, which is representing the median behavior, and we have the confidence intervals at 90% that is represented by this band. So what this means is that if I have a prevalence of 100%, meaning that in this case, all my products are contaminated, I will have here all this portion that is exceeding the threshold of 100 CFU or 2 logs. And this is 78% of my simulations, not my products, my simulations. Now, if I assume that the prevalence is 5%, then a simple calculation would tell me that the non-compliance would be 39%. Now, here you can see that we have access to new type of information that we did not have access to when we were considering only the microbiological analysis. Now, what decision can we take? Is it compliant? Is it not? I'm not going to answer to this question because it's really complex, and all I'm saying is that as a risk assessor, I'm just going to give this information, but it's the responsibility of the risk manager to take the decision. And risk managers most of the time are more comfortable with fixed assessments or simple results. And when they are in front of such results, sometimes they don't like it and they find it more difficult. So they don't use the tools that give such insights, which is a pity. And here I would like to refer to a publication, a recent publication, and I think some of the authors are on the call today, which is really good to discuss this notion of residual risk and to really know that zero risk does not exist, especially if we are going into this kind of distribution and probabilistic approaches. And here I considered only the variability. So think about it if you also add the layer of uncertainty. So to conclude, you can see that applying predictive microbiology in the food industry is challenging because of some reasons. So the so-called science push projects that we want to put in place are sometimes difficult to endorse. The scope can be very ambitious versus the available resources, and I'm happy to see this initiative of the Young ICPMF and also all the students that are with us today. So we really need more people trained on this topic. Of course, we need to do some internal advocacy to move the lines and bring a little bit of change. And yes, sometimes the discussions with the risk managers are a bit challenging because they really ask you, so is it safe? Is it not? And it's really difficult for them to make their decision based on the data. But this is also so fulfilling. So it means collaborating with really best-in-class academic teams. You get to interact with large and multidisciplinary groups within the organization. You have coaching and mentoring opportunities, and you have the satisfaction to drive change and to see business needs that are matched with really scientific outcomes, which is nice. So worth it? Yes, absolutely. And then I would like to leave you with this saying is that if you really choose a job that you love, even though you have a lot of challenges, you are lucky because you will never have to work a single day in your life. And with this, I will hand over to Anderson. Thank you.
Thank you, Marianne, for your very nice presentation. So we have questions from the audience now. So guys, if you want to make questions while the speakers will respond those that we got during the presentations, feel free, and I will read those questions to the speakers. So we have the first question that we have here is for Heidi. Heidi, this is a question from Ezekiel Green. The question is, does your students skip honors course? We have a degree, BSc, honors in microbiology, then master's.
Yes, yeah, thanks for the question. Yes, we have an honors program in Wageningen, but it's not like on top of the bachelor. It's basically an option for bachelor students. So if we have high potential bachelor students, they can apply for an honor program, which runs in the third year of the bachelor program, and then they work in quite multidisciplinary groups, not only on a specific food microfield, but it's with all kind of students with a biology background or environmental science background. So we have it, and they can choose if they want in that program also for one specific like small ECTS number, also on a more topic of the preference, which could be, for example, food microbiology. So we have it, but it's not like an integrated part of the whole curriculum. Yes, thanks.
Okay, thanks, Heidi. So the next question is from Johanna Ramirez. This question is to Marianne. The question is, she says, thanks for the presentation, very pragmatic. Can you please share why did you choose one for the physical state in the simulation with Combase for Bacillus cereus?
Thank you for the question. Yes, this is a choice, and most of the time we go fail-safe. So we say that there is no lag time because we have maybe not enough information to fix it to a certain value, and the value that is given in Combase is an average, and sometimes we would like really to be focused on the safety, so we put it this physiological state parameter to 1, not to have any lag time.
Okay, thanks, Marianne. There is another question from Ana Caroline Zaroni. The question is, how can we get access to FSSP and other softwares mentioned today? I think the question is, are all they free or do they have to pay to get access?
Yes. Hi, Anna Carolina. So FSSP is a free software and you can have access to it. If you want, we can share a list of the links. So Combase is also free. SimPrevious has some features that are free and some others for which you need to pay €120 subscription per year, I think.
Okay, very nice. I think this is a question that several people from the food industry has, whether they need to pay or they are free. Ana Carolina, I know her. She works for Coca-Cola, so that's why the question. Thanks, Ana, for your question. Thanks, Marianne, for addressing this. We have now 2 questions that I think I would like to hear from all of the speakers. You are free to respond those. These are from this guest, Queenet. We don't have the name of this person, but can predictive microbiology be applied to food fraud detection? So maybe this is a question that can be addressed by the 3 speakers. If you could share your view on this.
I'm not sure I understand fully the question. So can we use predictive microbiology to predict food fraud
detection? Yeah, I've never thought about it, but it's something to think.
So the definition of predictive microbiology is really to predict the behavior of the microorganisms. Now, for food fraud, my understanding, I'm not an expert in that topic, but it's that we would like to detect, for example, now we are talking a lot of plant-based, and then we don't want to find genes or animal proteins there. So I'm struggling a bit to see how the prediction of the microbial behavior could help us with food fraud, but maybe Heidi and Juka can complement that.
I think it's mainly like active in the field of the molecular detection, like DNA, different foreign DNA, not related, as far as I know, related, linked to the field we are discussed today, like prediction of microbial behavior. Yes, so as far as I know.
Yes, I have the same kind of feeling that I know one example in our authority. There was some fraud detection about strawberries, and it was based on chemical analysis of the strawberries, because depending on where they are grown, and there are a little bit different combination of chemicals and isotopes that are in the strawberries, depending on where they were grown, and so then you could actually detect if it was a domestic strawberry or imported from some specific geographical area, and that's possible, but I haven't seen predictive microbiology being used in that kind of context.
Thanks, Huka. So now another question that can be addressed by all the speakers. This is from Natalia Bus da Silva. She says, thank you very much for the very nice presentations. My question is for all the speakers. How is the interaction between the three fields, academia, regulatory agencies, government, and industry regarding predictive microbiology? Huka, maybe you could start this as it's somehow related to your presentation.
Sorry, could you recap a little bit? I was lost in the middle.
Okay. So the question is how is the interaction between the three fields, academia, regulatory agencies, government, and industry, regarding predictive microbiology?
It's as I said, it's the predictive microbiological modeling itself is not kind of a everyday job, but sometimes when the need comes, and there have been still quite a little direct connections with the industry. It's mainly about the government and then academia, but in research projects. But sometimes, yeah, actually in some research projects we had some small collaboration, but it was not very large extent, and so there were some data that they were providing to a research project.
Okay, thank you.
Yeah, and actually in Wageningen we have several projects where we collaborate with the government and also with industry in research projects. So there, I think there is a quite joint efforts basically with different angles from different perspectives in the three areas, also in the field of predictive modeling. Yeah.
So to add on that, I think the research projects are really a good opportunity to discuss this topic and to exchange ideas. Also symposia and, like IFP's PDG, for example, on the microbial modeling PDG is really a good opportunity because we have representatives from the different stakeholders, and it's good in time of peace, so there is no crisis, to have the opportunity to discuss. The standardization organizations like ISO is also a good forum for that, but I personally think that it would be really good to increase the number of forums where we could discuss those topics and how to make decisions so that we can all work towards the same direction to improve food safety.
Thank you so much, Marianne, and Heidi and Huka for addressing this question. And we have another question here before we conclude. That's from Larissa Margalho. This is for Marianne. Thanks for your amazing presentation. I would like to ask if there is any study of validation after comparing the conditions in FSSP, and if yes, how it's designed.
So the case that I shared today was completely out of my imagination, but in some cases it will depend on the authorities and the context. So if you need to present this to authorities, we know that some of them would be open to receive just simulation results, while we know others would be more willing to to give you their approval if it is supported by a challenge test or a validation study. So it really depends, but the models that are available most of the time are validated, and we use only those to make our assessments, and then there is no need for additional lab work unless the model is not really fit for the purpose that you would like to use it for. And in that case, yes, you would need to engage into validations.
Thanks so much, Marianne. So another question here from Fernando. This is to Ruka. How critical are the sensor data for mathematically assessing microbiological criteria? Is the main driver contributing to uncertainty?
That depends a lot on the bacteria and the matrix, because actually, yeah. For example, salmonella in some, let's say, in a risk assessment of eggs in Finland, it's kind of because the prevalence of salmonella is so low, it's somehow almost difficult to find salmonella positive samples to actually get the levels above detection limits. And so it's in some cases it's very difficult to even get an estimate of the distribution when almost all of the samples fall below the limits. And then of course it's kind of becomes critical issue that can you then somehow even model the distribution. And in some cases the situation is somehow paradoxically better if you have more higher prevalence and more higher concentration levels, then you get more positives and more bigger numbers above the limits, and then it makes your distribution estimation simpler. But I guess that as we go towards better food safety and all the prevalences are going down and the concentrations are going down, then finally actually we have a kind of assessment problem that what to do if all of your data is below the detection limits. And then of course that's a big uncertainty in that respect. But as I said, it's not the only aspect in the food chain. When you consider the whole farm to fork chain, and there are sometimes even bigger uncertainties about the distribution of the products and so on and their use.
Okay, very nice. We have, I think, two interesting questions here. We are going to do those two, and then we conclude. This is from Alex Puerta Gomes. It is also for you, Ruka. He says that you mentioned about R packages, and he's asking whether there is only one R package for food risk assessment, or it is a combination of different R packages. It is, you are muted, Ruka.
Oh, okay. So sorry. So that was one example would be like if you know the 2D simulation package. I guess one of the authors is Regis Puilo, and so there are some specific packages for specific models and applications, and so I think that there could be coming more of those that are somehow solving some particular problem in a context, and not one package for all food safety, but for specific problems, foods and hazard combinations. So I could see that there could be more useful R packages like the 2D simulation package.
Okay, thank you so much, Ruka. And this is the last question. This is to Marianne and maybe also to Hyde. Alex Puerta Gomes, are validation studies for predictive microbiology the same as challenge studies?
So this is a good question. So it depends. So validation studies for predictive models can mean many things. If you develop a model, usually you have a stage where you are going to generate independent data from the ones that you use to have your model to validate what your model is predicting. And then, of course, you are not going to produce a model for each individual product that you have, for example. So you might be doing some groupings, like putting, I don't know, dairy products together, meat products together, and so on. This is a very high level example. Huh? And then if your model was developed for listeria and dairy, you might think that it might not be exactly the same if you do it in meat. So this is where we are going to talk about validation to extend it to another matrix. Now, the way you do that most of the time is by inoculating artificially and then estimating parameters, for example, the growth rate and so on. So this is very close to what we call a challenge test. So challenge tests can be used to run validation studies. However, not all challenge tests are good to validate models. And I leave it to Heidi to complement.
Yes, and I think validation is not only related to the pathogens. You can also validate the shelf life related to spoilage. So it's I think it's used. The term used is I think a bit broader. And challenge study, I think it's really used in the area of risks of food safety related to pathogenic growth.
Thanks so much, Heidi, and also Marianne for responding those questions. So we are approaching the end of this webinar. I'm gonna now pass I'm gonna invite my colleague Ursula Gonzalez Barron. She's gonna conclude this webinar. Thanks so much, guys, for being here. I also I'm thankful to the speakers that were here with us today. Ursula.
Thank you, Anderson. So I'm Ursula Gonzalez Barron talking. I'm the secretary of the ICPMF, and I would like to say a few words on behalf of the ICPMF, and I take the liberty to say on behalf of the Young ICPMF as well. I would like to thank our invited speakers, Maria Melose, Heidi Den Besten, and Yuka, because they took the time to make these nice presentations and took the time to be with us today and share their experiences in predictive modeling from different angles. Also, I'd like to thank Anderson de Souza Santana for his availability for sharing, and Fernando Perez Rodriguez because he has been very much engaged in the technical organization and setting up this virtual meeting. Thank you to all attendees, among them the young researchers, the postdocs, and other colleagues that joined today. This webinar is going to be online on the website of the ICPMF. And if you wish to know more information about the Young ICPMF or even to join, just drop us an email. So thanks to all again and stay safe. Thank you.
Thank you, guys. Have a great weekend.
Thank you all. Bye-bye.
Bye, Ursula. Bye, Marianne. Bye, Luca. Bye, Heidi.
Thank you. Bye.
Bye.
Bye,
Thanks,
Fernando.
Anderson.
Thanks.
Bye,
Bye.
Anderson. Thank you, Anderson. Bye.